All right, so like I was saying, the squeeze theorem basically says that if we have these functions, then they are going to exist in this open interval, and that you can look at the limit of the outside, and get that that limit is the limit of the inside. It's really more used with trig. 95% of the squeeze theorem problems you're ever going to see involve trig, and they're pretty much going to involve these 4 trig functions. So these 4 trig functions you have to memorize. At some point in time, maybe in the future, we might prove that one of them is true. But for now, you have to believe me when I tell you that they are true, and you have to memorize that they are what they are. So I did show you kind of geometrically in that proof down below it how and why we get these values. So we know area of a triangle is 1/2 base times height, where the height is equal to the tangent and the base is equal to 1 because it's a unit circle right triangle. So that's how you get tan theta over 2. And then we go to our S equals R theta from our last unit, and the S equals R theta gives theta over 2. Therefore, the area becomes sine of theta over 2. And we can make this whole idea that it is going to live and be less than or equal to 1, which is why the sine of theta over theta, or sine x over x, is equal to 1. So in example number 1, we have the tangent of x over x. So if you have tan x over x, what you want to do is change that geometrically so that everything is in terms of sine or cosine. So tan x over x could become the sine of x over cosine x. And I can't get in. So sine x over cosine x all over x. This is why we got the trig identities. So now you have a fraction and a fraction, which we know is a no-no. So we're going to multiply by the reciprocal. So that this becomes the limit as x approaches 0 of sine x over x times cosine x. And then we know that limits can get broken up. That's what we kind of just talked about. So the idea is that you can look at the limit at the beginning and the limit at the end and mash them together. So this is equivalent to the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. Well, sine x over x we've memorized and learned to be 1 times 1 over the cosine of 0. Well, cosine of 0, if you think about your unit circle, is 1. So this becomes 1 times 1, or 1. So the limit is x approaches 0 of tan x over x, which also looks like an indeterminate form because you get 0 over 0, becomes 1. In this second example, what you notice is that the 4x doesn't match sine x over x. You have a 4 in your angle. So what we have to do is get a 4 in our denominator. So if I want to have a 4 here, algebraically, where else must I also have a 4? In the top. So in order to legally multiply by 4 on bottom, you have to multiply by 4 on top, because it's like multiplying by 4 over 4. So this is equivalent to the limit as x approaches 0 of 4 sine 4x over 4x now. Well, sine of 4x over 4x is the same as sine of x over x, as long as the number inside the angle matches the number in the denominator, that limit becomes 1. So as long as the number in the angle matches the numbers in the denominator, it becomes 1. So we just now have this kind of extra 4 hanging out. Well, a constant can get brought out in front of a limit. So that's kind of like equivalent again to saying 4, limit as x approaches 0, sine 4x over 4x, which becomes 4 times 1, or 4. Okay? 1 minus cosine squared x. Obviously, if we plug in 0, cosine of 0 is 1. 1 squared is 1. 1 minus 1 is 0. Plug in 0 to the bottom, you get 0. So, algebraically, what could we do to that? Yep. Alright. So, we could change this to the limit as x approaches 0 of sine squared x over x. And sine squared x is really like sine x times sine x, right? So that's kind of like saying a limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x. Because again, if you multiply back together, you get sine squared x. Sine x over x is 1. The limit as x approaches 0 of sine x would become sine of 0. Good. 1 times 0 is 0. Now, that's one way to do this. I actually thought in my head the first time I did this problem that the 1 minus cosine squared x was actually a difference of squares. So I, in my head, made it 1 minus cosine x, 1 plus cosine x. And then that became my rule on the front for the cosines, where it was 1 minus cosine x over x is 0. And I thought if this is the limit as x approaches 0 of that, times the limit as x approaches 0 of this, and again, you still end up getting 0 times 2, which is still 0. So again, we can all think and do math a little different, but the end result should always be the same. As you start to make me question my own answer keys. That comes in full and thorough answers. Okay, and then example 4, guys, that's a squeeze theorem. So you have h of x equals negative x squared, f of x equals x squared times 10 pi cosine, or times cosine 10 pi x, and g of x equals x squared. Use the squeeze theorem to show that that is all equal to 0. So once again, the idea is that you want to look at all 3 limits and their function values. So h of 0, f of 0, and g of 0. So all of their function values are equal to 0. The cosine of 0 is obviously 1. So if you use your graphing calculators to sketch this, you can show that the limit as x approaches 0 of negative x squared is equal to 0. The limit as x approaches 0 of x squared cosine and the limit as x approaches 0 of g, which is x squared. Now, the reason this one matters is because when you graph that, it becomes oscillating. And technically, you can't find the limit of an oscillating function. So we can plug it in and see that it works, but it's also an oscillating function. Because of that 10 pi x, it's rapidly shrinking down its period. So we have to know that this is oscillating. And your sketch on your graph, I'll have you guys sketch this. I can pull it up on my calculator if you want. But the idea is that as you look at that really, really closely, it's going to be going in here and getting teeny, 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 tiny. And then it gets like kind of big again. So when you smash it between the two x squared functions, it goes like this, it goes like that, oscillates between them. And as you zoom and you zoom and you zoom and you zoom, and eventually all sit together. We'll stop there. I'll do horizontal and vertical asymptotes tomorrow if everybody is free. So I want you to do circuit 2, because I like the circuits. I think they were very helpful. I like when you have like actual answers. So we're going to do circuit 2. And then a couple problems. Not many. Just use the picture.